finished our permutation formula and permutation R yesterday, where different objects taken R times could be written as this following formula, and we solved a example how to solve for n using this permutation formula. Now when we consider working with arrangements, we can consider solving the question either using the fundamental counting principle or and sometimes one lends itself easier to makes more sense than others, so I kind of go back and forth. So we'll talk about both ways. So example 7 here, it says how many 3-letter permutations. So when you see the word permutations, this means the same as arrangements. So how many different arrangements could be made if I pulled 3 letters out of all the letters in the word Kelowna? So again, these are like Scrabble tiles in a bag. I'm pulling 3 letters out. How many different ways could I arrange 3 out of these 7 letters? So fundamental counting principle is when we draw these spaces and fill in these spaces, right? We're filling this space with how many possible letters could I pull from, would be 7 times, I'm assuming there's no repetition, so there's 6 letters left in the bag to pull from, times 6 times 5. So our answer would be 210 ways. Okay, so this is using fundamental counting principle, which I tend to always go to rather than permutations, but either is totally correct. Another way to think of this is through permutations. You can think of, well, I'm pulling from 7 letters, permutation, and I'm taking 3 from those 7 letters. To solve this, your calculator will actually do this permutation symbol for you. So if you simply type in 7 math, go to the PRB, and then number 2 for PRN permutation R, and then type in 3, we get 7 permutation 3. Or you could go to your actual formula for permutations, which is n factorial. So I'd go 7 factorial divided by 7 minus 3 factorial. So 7 factorial divided by 4 factorial would be another option. So I'd go 7 math factorial divided by 4 math PRB number 4 for factorial. So again, I get the same answer. So really 3 different ways you could solve this question, all giving you the same answer. All right, example number 8. It says 6 actors and 8 actresses are available for a play with 4 male and 3 female roles. How many different cast members or cast lists are possible? So we will consider the male roles. So let's do the males. So how many actors do I have available to create a cast? Well, there's 6 possibilities. So I'm going to take 6. Permutation, and how many am I taking them? So I'm going to go 6 permutation 4, which gives me so 6 permutation 4 gives me 360 ways. So this would be 360 ways I can create the male cast, and then I want to create the female cast. Well, how many actresses do I have? I have 8, and I'm taking 3 of those 8. I go 8 permutation, and this would be 336 ways. Now, what do I do with these 2 numbers? So, key wording in the question, when it asks for how many casts are possible when 4 male roles and 3 female roles, this word and means to multiply my values together. So I want to multiply these. My total would be 120,960 different cast lists are possible. Okay. All right, example number 9. It says, find the number of permutations, so again, possible arrangements of the letters in the word kitchen if the letters K, C, and N must be together. So this is when we start to get into restrictions, and as soon as we start to get into restrictions, I tend to always go with fundamental counting principle. It just makes more sense in my mind, but permutations is also possible. So it says that the letters K, C, and N must be grouped together. So they are going to take up kind of 3 spots together. This has to be a K, a C, not necessarily in that order, but that is going to take up a space in this arrangement. So we're going to clump those together and think of they are taking up a position in the ordering of the letters. So this is one position. I then have what letters to arrange left over. I have the I, the T, the C, the H. The I, the T, the H, and the E. So I have 4 letters left to arrange. So I have 4 letters left to arrange. So technically I have 5 possible spaces or positions that I'm arranging. So if you think of this is a letter, and then I have 4 more letters. Technically, these 4 letters could be arranged as 4 times 3 times 2 times 1, which is technically just 4 factorial. These letters aren't necessarily going to go in this order. It could be a C, a K, and then an N. It could be a K and then a C. So how many ways can these 3 letters within themselves? This would be 3 factorial. So I'm going to take 3 factorial times, and then how many positions could this group of KCN go into? Well, they could take the first position, the second position, the third, the fourth, or the 5th position. So I'm going to then multiply this by 5 is the number of positions possible. Okay, so my answer would be 3 factorial, 4 times 4 factorial, times 5. So 720 different ways. All right, question B. It says, how many different arrangements of the word kitchen can be arranged if the vowels must not be together? All right, there's honestly no other way to figure this out unless you actually found all the possible ways that the I and the E cannot go together. So what we're going to do is we're going to calculate this. Using what we call the complement. And what the complement is taking the total number arrangements with no restrictions minus the arrangements. So we're going to take away the arrangements when the vowels are together. So the complement is calculating the total minus the opposite of what the question's asking. So if we don't want the vowels together, well, we're going to figure out how many arrangements would there be if they were together, and then subtract that from our total. So the total number of arrangements to arrange the word kitchen, again, these are like Scrabble tiles in a bag. How many possibilities do I have for the first letter to pull? There's letters to pull for the first, times 6, times 5, and so on. So the total number of ways to arrange the word kitchen would just be 7 factorial. Minus, now we have to figure out the number of ways, well, the vowels would be together. So similar to this, the E and the I are going to be together. So they are going to take up like a space in their own in their arrangement. There are then 5 letters left to arrange. So these 5 letters can be arranged in 5 factorial different ways. The E and the I within themselves could be, it could go in the E and the I, or then the I and E. So these can be arranged in 2 factorial different ways. And then how many positions could the E and I go in? Because it does not say the vowels have to be in the front. They take the first position, second, third, fourth, fifth, or sixth position. So I'm going to multiply this by 6 positions. So on our calculators, 7 factorial is 5,040. 2 factorial I know is just 2 times 1, so I'm just going to put 2 in there, times 5 factorial. Oops. Which is the number of positions. So 1,440. So it's going to take 1,440 different ways to arrange the letters if we put the E and I together. A total of 5,040 ways if there is no restrictions at all. So if we subtract the 2, we get the total number of arrangements, which would be 3,600 different ways to arrange the letters when the I and the E will not be together. All right, the last thing with permutations is permutations with identical objects. So if you think of these 2 words, cat has 3 different letters in it. We could arrange this in 6 different ways. We could arrange E-A-T, C-T-A, T-A-C, T-C-A, A-C-T, or A-T-C. So this is 6 ways, right? Or using fundamental counting principle would be 3 times 2 times 1. But what about the word boo? So for example, this has the same number of letters, but we have 2 identical objects happening. We have 2 O's in this question. So if we said this is a subscript O2, if I rearrange this like this, does this word really look, is this arrangement really different? And the answer is no. So you actually have to consider identical objects. So how many ways could we arrange this? Well, boo would be one arrangement. O-B-O would be another arrangement, or oob, O-O-O-B would be a third arrangement. So this can be found in 3 ways. So as soon as we start to work with identical objects, what we want to take is we want to take the total number of ways to arrange all 3 Earths, which would be 3 factorial. And then you start to divide it by your identical objects. So in this case, we have 2 O's, so I would divide this by 2 factorial. So 3 factorial divided by 2 factorial leaves me with 3. So that's a short form of that 3. So in general, the number of permutations of n objects where A are the same of one type, B are the same of another type, and C are the same of yet another type can be represented by the following expression. So if you take n factorial and simply divide it by all of possible identical objects, then this will give you your solution. So in this case, we only had 1 set of identical objects, which are the O's, but you might end up with more, right? So that's where the A, B, C's, technically D's, E's, and so on could come. All right, so we're going to look at one example, but we're going to go through like 5. How many 7-letter arrangements of the word poppies, so here's our word, can be made under each of the following conditions, assuming all the letters must be used. So we can't repeat letters. Okay, so even though it says without restrictions, right, I can't arrange this by just swapping these two p's, and that wouldn't become another arrangement. So even though it's without restrictions, I still have to consider identical objects. So how would I solve this? I would take the total number of, so that would be my n, so I'd take 7 factorial, and then I'd divide it by my identical objects. Well, in this case, the p's are the only set of identical objects, so I would divide this by 3, and there's 3 of them, so I'd divide this by 3 factorial. So the answer would be 840 different arrangements. Now, question B, if each arrangement begins with a P. So there are several different ways you can think about this. Depending on your thought process, I'll show you how to solve this in 2 different ways. So one way you can consider this is this first letter has to be a P. So you can think of this as I am going to take one of the P's out of my bag of Scrabble tiles. Okay, so I'm going to take it out of the equation completely. I'm taking a P out of here, so let's take the first P, and I'm placing it in this first position. So it's like a fixed object. This is not moving. Then, how many letters do I have left to arrange? Well, there's only 6. So now I'm going to take this and multiply it by 6 factorial, because that's how many positions are left, 6 factorial. But then I have to divide this by my identical objects. But in this case, because we took one P completely out of the equation, we put this here, and we're really only 6 letters, technically my identical objects would only be 2 P's, not 3. So I'd divide this by 2 factorial. So that's one way to think of it. The other way to think of it is you could say, well, I'm still picking from this bag, but a P has to go there. And so some students might think of this as, well, there's 3 possibilities that could go there. There's 3 P's to work from. So and then times, I'm using up one of those 3's. So how many objects are left to arrange? There's still 6 letters left in the bag. So I'm going to multiply that by 6 factorial. And then I'm going to divide that by, because this is not a fixed object, you're considering it as a possibility of 3 P's, identical objects here. So in this case, we would divide by 3 factorial. So our answer should be 360 ways. Okay, so 2 ways to think of it all the time. All right, question C. If the first 2 letters are P's, so the first 2 letters are P's. So the first letter is a P and the second letter. So again, you can either consider, okay, this first position has to be a P. A P has to go there. So I'm going to take one of these P's out of this group of letters and put that here. So there's one possibility that can go there. This is like a fixed position. I'm going to also put a P in my second position. So again, I'm going to take another P out. I'm taking that away. So there's only one P that can go there. This is again fixed. So I'm not even considering this right now. Now, how many letters are there left to arrange? Well, there's 5 letters. So I'm going to divide this by 5 factorial. And then, are there any identical objects left to divide by? And technically they're not, because we took away 2 of these P's, and technically I'm just arranging 5 letters now. So my answer would just be 5 factorial. Or, the other way you could think of this would be, how many possible P's could go in this first position? Well, there's 3 of them. Times, how many possible P's are left in position? Well, I've used a P here, so now there's only 2 left over. Times, how many letters are left to arrange? There's 5, so 5 factorial. Divided by, again, because we're considering these within our arrangement now, I would consider all 3 of these P's as my identical objects. So my answer should be 120 ways. Okay? So whether you think of the identical completely as a fixed position, or you include them in your arrangement. Both are correct, but you should get the same answer. But here we didn't have to consider identical objects because this was fixed and fixed. Here we did because we're thinking about how many possibilities are there. All right, question D. If all the p's together. So again, two different ways to think of it. You could think of, okay, I'm again taking all these p's out of the equation. I'm lumping them together. I really can't arrange these in any other order, so this is fixed. This is 1. How many letters are there left to arrange? Well, there's 4 letters left to arrange, the O, the I, the E, and the S, so that would be 4 factorial. But technically, let me show my position. So the p's are going to take a position. There are 4 positions left, which would be 4 factorial. But does it say the p's have to go at the start of the arrangement? No, they could go in the start, the next position, the 3rd position, the 4th position, or the 5th position. So I'm going to multiply this now by 5 positions. Do I have to divide this by identical objects? And the answer would be no, because I've fixed these together as just one group. I don't have to consider how these p's are arranged because there's no other possibility. These are fixed. I don't have to consider identical objects. Or the other way, well, how many ways could I arrange these p's within themselves? And within themselves, I would arrange these 3 factorial different ways. Times, I have 4 more letters to arrange, so 4 factorial. Times, how many positions can the p's go into? There's 5 positions. It's because we're considering arranging these p's in different orders, these I would now have to consider my identical objects. So I'd have to divide by 3 factorial. So technically these 3 factorials cancel, and my answer is 120 ways. All right, and then lastly, if the first letter is P and the next one is not a P, so this is a little bit different. So the first letter has to be a P. So again, I can consider this as a fixed position. I'm taking 1 P out of those letters, that word, and putting it here. It's fixed, it's not moving, it's staying there. Then it says the next letter behind that is also a restriction. It says it cannot be a P. So how many possibilities would go there? The O, the I, the E, or the S. So there's 4 possibilities. And then the 3rd position doesn't matter. The rest of the positions doesn't matter. So I've used a P here. That's completely gone. I've used the O, the I, the E, or the S here. So that's gone. So how many letters are there left to arrange from here on in? There would be 5 letters. So 5 factorial. And then I would divide by my identical objects. But remember, we took a P completely out. We put it in this fixed position. So technically there's only 2 other P's that we have to consider, identical objects. So I divide this by 2 factorial. Okay. Or another way to think of it is, well, this first position has to be a P. So you could think of this as, well, there's 3 P's to choose from that I could put there. So there's 3 possibilities. Times this next letter cannot be a P, so that would still be 4 possibilities. Times how many letters are there still to arrange? Well, I've used 1 P here, I've used another letter here. There's going to be 5 letters left to arrange, which would be 5 factorial. And then I would have to divide this by all of my P's because I'm considering all the possibilities here. I'd have to divide this by 3 factorial as my identical objects. So my answer should be 340 ways when we multiply these. Right, so that is the end of permutations.